here. Okay.
Sir, may I ask doubts about graded assignment?
Of week 8.
Yes, recent
Okay.
one.
Yeah, tell me.
Wait a minute, sir.
So maybe we'll take up his doubt and thereafter we can start our usual session.
So question number 11. I didn't know how to apply those linear approximation rules there. I don't have an idea how to solve that question.
Okay, so we'll provide you the solution, then you can just have a look at it, right?
Yeah, I checked for solution, but it wasn't available right now.
Yeah. That's what, like, we'll provide you. Maybe by today we'll provide you. Okay.
Okay, but sir,
Then you
could you
can.
just explain how to approach that sum?
Sure. It's question number 11, right?
Yes.
So for this particular question, you have been given a function p, which is from R to R, right? That question, isn't it? Hello.
Yes. Yes, sir. It's a step. It's a stepwise function, I guess. Interval-wise function.
And then you have been given a linear function, which is nothing but at plus b, denotes the linear approximation of this function p of t at point
T
t
equal
equals
to
to
1.
1. Then
Yes.
find the value of, so if you know the value of a and b, then you can simply substitute the value and get, right? So how do you do the linear approximation problem?
Just like how we find the tangent.
Right. So the way you do it, right? And they're saying you at point t equals to 1, isn't it?
Yes.
So since they are telling you, they are pointing at t equals to 1, so you can you know how to find linear approximation. You have the standard formula, right? And then you can simply substitute this value and get the value. Then you can correlate, okay, what is the value of a and what is the value of b. So a indicates that slope and b indicates that your intercept value. So intercept here means what? So how
Okay,
do
it
you
is in a
write?
form of y equal to mx plus c.
Yeah, so you just have to equate that and get the value of a and b, and you will get the answer, right?
Okay, sir.
Yeah. Okay. So maybe I'll just start with our normal session. Yeah. So I think yes, some of you joined here.
And sir, could you just tell me how to take derivative of this 7 bracket t square minus 49 whole to power 1 by ln of t minus 7? Like,
Uh,
I think this goes to power infinity, right?
which one?
Again, question number 11.
How to find the derivative? Is it? Okay, just let me have a look at it.
Like, we were supposed to check continuity, right? Somewhere. Yeah, in question number 10, we were supposed to check continuity and differentiability for this function.
Oh, okay.
So,
See,
like the
what you can
last
do
option.
here, last
Okay.
option, neither p of t and nor q of t is continuous, right?
No, nahi, the last interval t is greater than 8. For that, like how to check, like
T is greater than 8. For me, it shows, yeah,
if you
okay, fine.
if you substitute t equal to 8, then ln of 0, it becomes ln of 0, which is like 1. Okay. Okay, I get it. Sorry.
You get it? Okay. All right. So don't worry, we'll provide you the solution. Then I think all your doubts will get clear. And even we missed out to provide you the solution. So maybe by today we'll provide the solution for week 8. Okay. So you can see my screen.
Yes, sir.
You can see my screen, right?
Right, sir.
Yes, sir.
Yes, sir.
All right. Okay. So now we are now we are entering into week 9, right? So what do we see in week 9? What are some of the content? So let's just discuss that, like what are some of the concepts, and then we can take up some of the questions. So in week 9, this is like AQ session. So let's see what we can do here. So you see in this, what do we what are like contents for this week? So you know that
Yeah,
since
maxima, minima,
right.
local maxima, minima.
Fine. So it is more about finding local. I can say it is. You can say that it's kind of, you are applying derivative concept here. So
Is the
that is one
application
thing.
of derivation,
Yeah.
application
So
derivative.
and then the second part of it is about integrations. So over here in integration, so you know that integration can be done by the various methods. So here not all methods are discussed, but some of them. So we can see those. What are those things first? So first, local maxima and minima, of course. That these concepts, let's see, we can discuss this concept today. Then what are some of the boundary points? So all these things seems easy when I write, but when we do some problems, then you'll find out, okay, this is something which we are missing out. And then so let's discuss some of the conceptual problems where we might go wrong. Okay, so that is something we'll do. Okay, so what about this and because that is where even we catch you, like even though the concept is easy, but we know like there are certain grave area where we can catch you where your concept might not be clear. So that is something we are there. So what I felt was we can discuss some of the concepts where we actually make mistakes. Okay, so first is what local maxima and local minima. Second is like we talked about, like you will see in the lecture that it is about boundary points. At boundary points, what is this maxima and minima thing, right? So that is something we can see, maxima or minima. We can discuss some of the
And the
questions.
critical point and saddle point is
Right. So yes, even those we can write. So this is like critical points. Then you have, so this is
saddle.
three. Then yeah, in this itself we can cover that saddle point. Then we do that second derivative test. That is something I can write it down explicitly here. Second derivative. So I think all of you might be knowing this, but we can discuss in a different way. Maybe I'll not stress more over here. Then what do you mean by global maxima and global minima? Those things, right? So we can discuss those things as well. And then, like then you have, now we are entering Riemann sum. So there is something which I don't remember that we ever learned it. Those who are from maths background in 11th and 12th, I don't know if you know this.
No, sir.
So that is one concept which is being introduced. So basically what we do integration is
Sir,
this
could you
concept.
just repeat what he just said? Because your voice broke off.
Okay, so what I meant to say was, basically, I don't remember that we ever learned Riemann sum in 11th or 12th standard, right? So we just jumped into, okay, what is integration and how it is done, right? But the main concept behind those integration is this Riemann sum. Okay, so that is something which we should actually learn and appreciate. Okay, that this is what it happened. So we can discuss this Riemann sum. So it's basically tells you like, okay, how is this integration thing happening and like what does it really mean? Okay, so this Riemann sum gives you actually insight about the integration, and then you can jump into actual integration. So again, now in integration, what do we have? Now we have more on, like, you have definite integrals, right? So you have some like definite integral, right? So it's basically you'll be given some limits, and basically some interval in which you have to find out the area, or you may, and also some kind of integration where you just have to integrate it, but this is application thing. So I don't think so it's just integration will ask you, but some kind of applications, right? So you see that, then what is this transition happening from Riemann sum to definite integral? Because definite integral, or let's say integral in general, we know what it is, but how do we jump from this Riemann sum to integral? That is also interesting to know that what exactly it means. Okay, then you have some standard integration formulas, right? So uh, that is something, it's given, and I think it is discussed in the lecture as well. So standard integration formula. So it's basically it's coming out of from here applications of this, and then you come up with the standard integration formula, and then you come over here. Right? Then you have integration by parts, then integration by substitution. Right? So these are the only thing which I think we will be doing for this particular course: integration by parts, and then we have integration by, maybe I can write it as second heading, integration by substitution. But you see there are various other methods like integration, by breaking a function into its parts by, you do it parts by parts, and there are various other ways of doing integration which is not being discussed for this particular course. So extensively these are the things, and I'll try to see that I'm doing some problems on all of these, at least. Yeah, I'll try to cover some of the questions in all of this, so that you will have an idea that okay, how to approach a particular question. And coming to the theory part, I think you can see the lecture and understand from there, but I will give more emphasis to question solving here. So that is something we'll do here. So we can just start with our thing.
So we don't have indefinite integrals.
We have it, right? Definite and indefinite, right?
Okay,
It's
we have
basically,
both.
so both comes into, because when you are finding definite, you have to, actually you have both, but it's not been explicitly mentioned here. So you can just take that in that. Okay.
Okay.
So now, yeah, so let's just discuss some of the conceptual problem and understand what it is. So first, as I told you, it's about, what was the topic? First, it's about what is this thing? What do you mean by local maxima, and what do you mean by local minima, right? So what is the definition for local maxima, and what is the definition for local minima? And then I can just discuss what is a critical point, and then we can take up one question, right? So just be with me. So what do you mean by local maxima? So if I write local maxima, I believe that you can write down what is local minima. Okay. So what is local maxima? So the definition is f of c is greater than just a minute. Okay. Okay, sorry for this inconvenience. So yes, so what do you mean by local maxima? Okay, so how do we say this? Now, let's say there is some point C, okay? So that f of c, if it is greater than or equals to f of x, for all x belonging to c minus h, comma c plus h, okay? Now this, of course, when I'm writing this h is nothing but a small interval, right? So that h has to be greater than, right? That h has to be greater than 0. And of course, this function f is to be a real valued function, right? So f is a real valued function. So this is some understanding, but what do you really mean by this? So let's understand this local maxima. So maybe I can just take first one contrary example and then discuss this. Okay, so now let's say this is one curve, and let's say this is my x-axis and this is my y-axis. So let's say this is some interval. Let's say this is my C. Okay. So then what is this corresponding thing? This is going to be f of C, right? Now let's say if I take this as this is h. So what is this? This is C plus h. And likewise, if I take the same interval over here, so this is going to be C minus h. Okay. So now you see this. What do I say from the definition? Local maxima definition is f of C is greater than or equals to f of x for all x belonging to C minus h to C plus h. So what does this actually means is this means this interval, right? This means this interval, isn't it? C minus h is this part and C plus h is this part, right? So essentially it means in this interval, what is the local maxima, right? That is what it means. So now if we look into this part, so when I say that f of C is greater than or equal to f of x, but do you look at this interval? In this interval, is my f of C greater than or equal to f of x? The answer is no, right? It is not here, because you see, if I take any value over here, this is giving me some greater value, right? This is going to give me some greater value, which is going to be f of C. For f of C minus h, I get some greater value. It's basically some, let's say this is my 5. So let's say this is going to give me 6, right? Likewise, if I take this one, so it's going to be 6 again, right? So you see this in this interval, f of C is not giving me greater than value, right? It's giving me lesser. So I can say for this point that this is my local minima, right? This is going to be my local minima. Okay, so now we also have sometimes this confusion. What do we mean by this local minima and the point of local minima? So just for the clarity, I would say here, clarification that when I say point of local minima, then it means point, that is x value, and local minima value, then I say that the exact value of f of C, right? So now look at the other example. So if I take the same curve but bit inverted and look at this part over here.
Sir, can you please tell that point that what is local minima? This is the range or this is the point? I'm confused.
So when we say generally local minima, it actually means that point.
All the points between C minus h
No,
and
no,
C
no, no,
plus
just
h.
the point.
Just the
point.
C point where this is maximum,
Yeah.
the thing is
Local
minimum.
minima, yeah. So over here, local minima is x equals to 6, and local minima value is what? Local minima value is f of C basically, right? So just to make it sure, so we can say that point of local minima is better to say point of local minima, or simply you can say local minima, that is nothing but C, and over here local minima value is f of C. Now over here, look at this again. Now this is
Sir,
yeah,
one thing.
yeah.
It's always happen at a curve, at turning point always. Like
it always
minima
happens
or
at turning point.
like
That you can say,
next.
yes, that is basically an application of it. But you also have this concept for the boundary points. It need not be a turning point, but at boundary points the definition changes. So maybe I should rightly say here local minima not at boundary point. So maybe I can just give a bracket, not at boundary point. So this is one condition. So that is basically, I'm not taking a boundary points here. I'm just taking any values. For that, then definitely it has to be some kind of turning point, right? Then you can
That time, if always happen at a turning point, so can I say we can about vertex, like can I relate this thing to vertex of parabola?
of course, for this particular example you can say, but if I have to give you another example, let's say you have example something like this. Can I call this as a turning point?
No.
I cannot call this as a turning point, but there exists a local minima at this particular value.
Okay, if the graph is not continuous or something, it's related to maximum minima thing.
That's what I'll come to this part when I'll take up some more example. Okay, so now you see this. This is going to give me what? This is going to give me f of C value, and if I have to take some, this is going to be my f of, if this is my h and this is another my h, so this is going to be, sorry, so this is going to be C minus h, and this can be C plus h, right? So now you notice again, like if I have to just extend this further and then I have to write down, so this is going to be C minus H, and also you can say C plus H basically. So you see that within this interval, what is the maximum value that I'm getting at f of C? That is why that is called as point of, that is why it is called as local maxima at C, right? So f of C is local maxima value at C. I hope you understood, right? So there is no problem with this definition here, right? So if f of C is greater than or equal to f of x for all x in this interval, this basically indicates an interval, right? So you have C in the center, and then you have some value being subtracted from C and some value being added to the C. And in that interval, you see that the C should give me the maximum value. F of C should give me the maximum value. If that is happening, then I can say that yes, that is a point of local maxima. Okay, so now let me discuss another example. So basically, this is not a point of local maxima, right? This is not a, maybe I should use different color so that, yeah, this is not a local maxima, right?
Why, sir? Not okay.
Not a local maxima in this interval, basically. This is not local maxima, it's giving you local minima, right?
Sorry, local minima, yes.
Yeah, over here, this is giving you local maxima,
Yes, got it.
right? So I can say this is giving me local maxima, and it is understood that when in this interval, you can mention that always, so that this is going to happen in C minus H to C plus H. Now let's take another example and discuss this local maxima and local minima. Then our concept gets clear with this. Okay. So now if I have to take another example, so let's call this as example 1, this is example 2, and discuss example number 3. Okay, so this is going to be our example number.
You are mute.
Yeah. So in example number 3, let's discuss some of the breakage point where we see this. Right. So now look at this part. Let me say this goes like this. Okay. Now this is another function. Let's say this is my C. Okay, and this is giving me some output, or let me use some numerical value. So this is going to be 5, and this is going to be, let's say, 10. Okay, and this is over here somewhat like roughly 10, maybe I can say that it's roughly not 10, but let me say it's going to be roughly 8. All right. So now I hope you understood what is local maxima concept. Then what about local minima? As per definition, it has to be lesser than, right? So if I have to write down local minima, then I have to say that f of C is lesser than or equal to f of x. Rest all everything same, right? It's just that for local minima. Okay, so now you just have to say me that for this particular function, let's say this is some function f of x. Okay, so you have to tell me for this particular function, is this a local minima in this interval? Let's say the interval is, maybe I can give some interval. Okay, so let me give it as 3, and let's give this as 6. So now this is going to give me some value over here. So let's say this is going to give me 6, and this is going to give me, so I have taken this interval. So let's say this is going to give me some output. Let's say this is going to give me 9. Okay, so now you have to tell me, do it have a local maxima at x equals to 5, or local minima at x equals to 5, or neither? So C is basically neither. Okay. So now you have to choose one. Okay, so choose the correct option. So could somebody tell me what is the correct answer?
First option is local maxima.
Local maxima at x equal to 5 is true,
It's true.
I think.
Okay, so can all of you mute, because I can hear my own voice coming from maybe YouTube or something. So yes, so let's discuss this concept. So how is this happening? So this is my X, this is my Y, and you can see this is our curve. So maybe I'll be using different color. So use this. Okay, so now you see this. Is this going to happen? So f of x has a local maxima value at x equals to 5. So let's just check that. So our interval is something between 3 to 6. Right? So this is my interval. So in this interval, let us see whether this 5 is giving me the local maxima value or a local minima value. Okay. So now you see this in this interval, right? So if I have to just graphically check, how does it happen? So you see this, all that for local maxima, all that definition says is f of 5 should be greater than or equals to f of 3, right? So this is what I have to check, right? And there should be an and condition, and f of 5 has to be greater than or equals to f of 6. If these two are happening, then I can say this at x equals to 5, f of 5 is a local maxima value, right? That is what I can say, right? This is as per the definition, isn't it? Because it's the same thing in this interval. So what I'm doing here is just that I have been given some numerical value, so I'm just directly substituting it, and I change that definition slightly bit as per the convenience of the question, right? So you can understand, right, this part, how I have written this.
Yes, sir.
Okay.
Yes, sir.
So having known this, so what is f of 5? Could someone tell me what is f of 5?
5,
It's 10.
10.
10, sorry, yes.
So 10 is greater than or equals to f of 3. What is f of 3 value? 9.
9.
9.
9.
Let us check the AND condition, the other one. Again, f of 5 is nothing but 10. Is 10 greater than or equals to f of 6? The answer is yes. Again, this is happening. So if these two, again, if it is happening, then I can say that at x equals to 5, or basically at x equals to 5, the local maxima exists. So this is local maxima. So now look at this function. This is not even continuous, but yes, this is a continuous, but this is a function first of all, but this is not a continuous function, right? Right? And
Yes.
also
sir.
the limit does not exist at 5, and it is not continuous at 5. So it is not differentiable at 5, but still the
Yes.
local maxima condition or this definition fulfills here, right? So we should not go with this assumption saying that the function must be what? Differentiable, then only I can apply the concept of local maxima or local minima. So if you have this, in your mind, so remove it, because your local maxima and local minima concepts are independent from the type of whether it is a continuous, whether the limit exists or not, and whether the function is differentiable or not at that particular point. Okay, so I hope this concept is clear to you. Okay, now let us discuss another example. So now you see this, so as you rightly told that this is right, so this is wrong. So if any of this is correct, so neither is not correct, right? So now look at another example where we can actually see
Sir, like, just a second. Then for the second graph, what is the minima?
here there is no minima. I mean, see, basically I'm not fixing my value here. So as I told you, this is something I'm not discussing at boundary point, right?
I didn't get that boundary point thing.
Boundary point means this ending point, this end points.
Okay. Okay.
These are the boundary points. So I'm not discussing at over any places. So if I let's say if I have to check the same thing, or maybe I can take that as an example number 4. Okay, where so let's do this and then you can understand this better. So let's say this is, I'm taking example number 4. So you see this, let me say I have any curve, something like this. Okay, and this is my C over here. Okay, so this is my, or maybe I'll come to this first. Let me finish the other part of this and then I'll discuss this, so that we'll go in the flow and understand this concept first, and then I can give one contrary example to give you a better insight of this definition. Okay, so now look at this part. Maybe if I have to take this, so same function I'll take. Okay, so it's going to be like this. Okay, maybe not that, but this one. It's basically the same function I'm taking, but look at something I have changed here. Okay, so this is my f of x. let's say this is my x, and this is my again 5. Maybe I can say this is 5. Let's say this is 6, and let's say this is 3. And look at this part. This is going to give me, again, I can just substitute the value. So this is 10. Let's say this is 9. This is okay, sorry, this is, I cannot say this is 10 because so this is going to be, this is roughly 10, because I cannot exactly say what is the value, because this value is, you cannot exactly predict what is the value, right? Because that will be varying. So I say this is roughly 10. Okay, over here, let's say this is going to be something like 8, or let's say over here this value is something like 6. Same again, 3 conditions you have. At x equals to 5, there exists local maxima. Maybe I can say there exists local maxima. Same thing, local minima. And third condition is neither. So could you just quickly solve this and tell me?
Neither.
The point is open here.
Okay. So let's see, what do you say? Some of you are saying neither. Okay, so we can understand that why you are telling that. So
Sir, because f of 5 is greater than
just a minute. Let me take up the other call, and then we both can discuss this. Okay. So do any of you have got any other answer?
No, sir, meeting also there.
Okay, so even you, okay, so fine. So who was discussing with me earlier? What's your good name?
Deepa.
Yeah, Deepa. So let's go ahead with this. So so yes, so let's go with our definition. Okay, so now
Yeah.
what do I have to check for local maxima? What do I have to check?
F of 5 must be less than f of 3.
Less than or greater than f of 5
Greater
for
than.
local maxima?
Acha, greater than, yes, sir.
So first let me write down local maxima, and then we look at a local minima condition. Okay, so f of 5 has to be greater than or equals to what? F of
F of 3.
and f of 5 has to be greater than or equals to
F of
f of 6. Okay, so let us write down the corresponding value. So what is f of 5?
F of 5 is 8.
8. So is 8 greater than or equals to f of 3? What is f of 3?
Is 9.
9. So this is wrong.
Yes,
So it
sir.
is not local maxima.
Yes.
Now let us look at local minima. Okay, so in local minima, what does it say?
F of 5.
So I'll just write down this definition. So f of 5 should be lesser than or equals to f of 3, and f of 5 should be again lesser than or equals to f of 6, right?
Yes, sir.
Right, so it has to be lesser than or equals to f of 6. So what is f of 5?
8.
F of 5 is 8. So is 8 lesser than or equals to f of 9? So how did we get this f of 9? F of 3 is 9. So look at this. For 3, I'm getting 9, right? So f of 9. So yes, this is fine. What about the other AND condition? What is f of 5 again? 8. So is 8 lesser than or equals to f of 6?
No, sir.
Yes, it
No.
is 6.
No.
Okay, so this is basically greater. So this is not right again, right? So this violates both the definitions. So it is not local maxima and it is not local minima. So you can see from here, so this is not local maxima and this is not local minima. So this is neither in this particular case. So you understand now?
Yes,
You
sir.
understood? You got some insight, right? So just by looking at the graph, can I say anytime that yes, this is local maxima, this is point of local maxima, this is point of local minima? Of course, I can say with this. That will happen once you practice like 3-4 problems, or you can just do these problems only. Just do it and try to do it by looking at the graph, and then you should be able to do it. Okay. Now let us look at this local maxima and local minima concept. Yes.
Can we say in this graph there is a local maxima? It is not at 5, but it has like 4.999. Can we say that?
At 4 point, yeah, but again, that is not fixed, right? Because whenever you say 4.999, there'll be a third person claiming that yes, there is a 4.99999, right?
Yeah, so that is my question. Can we say
yes.
like the graph?
No, you cannot say that.
Okay.
Yes.
Thank you.
Yeah. So let's go with the next one. So example number 5, and let's actually exploit this. So I'll discuss this and I'll discuss one more, and then we can just finish it off. Okay. So now let's say maybe I have the curve similar to the first one, but my C is over here. Okay. Can I call this C is a point of local minima or local maxima?
No.
Anybody, any other answer?
With respect, sir.
If interval is given, we can say.
Okay. So the interval is this.
Okay. Then we can
One ratio.
we'll give you an interval. Yeah.
In this given interval, is this a point of local minima or local maxima?
Neither, sir.
Local minima.
Neither, sir.
Neither,
Neither.
sir. Neither.
Neither.
Neither. Okay.
Okay, but how some of you are saying local minima? So let's look at someone who is saying that, okay, this is local minima. Okay. So for local minima, what should happen? F of C should be greater than or equals to F of C minus H. And F of C should be greater than, lesser than or equals to F of C plus H.
Hmm.
Right? What is F of C? F of C is some value, right? So this is, let's say, see, whenever you solve this, just give some random value. If this is 8, this is 9, and let's say this is 7, right? So what is F of C over here? So F of C is 8. Is 8 lesser than or equals to F of C minus H, which is 7? No, this is gone here itself.
Okay.
So you understood,
Yes, sir.
right? So you cannot have this local. So I think you only had this doubt, right? At any other point. So that is why I came up with this. So I thought of discussing it here. So fine. Now look at the other part of it. Maybe I can just exploit it at somewhere else. And what can you talk about this? When I have a curve like this, let's say this is my curve. Okay. So this is happening at 5. This is F of 5. Let's say this is basically 10. Okay. So, and let's say this is my 5. So at 5, I'm getting some output 10. So is this my local minima or local maxima?
Neither, sir.
Tell me.
Then the both the things are equal, like C minus H, local.
We can say that
It be both.
it would be both, sir, because in
Yes.
definition it is less
this
than
is
or equal to
all
or
the
greater
values
than
are
or
same.
equal.
C minus H and A, C and H, all values are same here, na sir?
So could you tell me, like, no, you don't have to give me the interpretation. Just tell me whether yes or no for this.
No, I think.
It's
Yes,
neither.
yes. Izukalni
Both,
is
sir.
there.
Both
It's be
maxima
Izukalni
and
is
minima.
there. Both are
Minimum
exist.
maximum.
Both exist.
Both exist.
Both exist because it fulfills the definition of both, right? What is the
Yes,
definition?
the equal sign is there.
Equal sign is there, right? So in that particular equal, if that is there, then yes. And even for local minima, yes, you can say that it exists, right? So similarly, so I think now we have discussed all possible places where we can discuss this, right?
Yes, sir.
So I don't
Get
think so
it.
you can make mistake anywhere now in this critical, at least in this local maxima and local minima places, right?
Yes, sir. Clear.
Okay. So now having known that this is clear, let's discuss at boundary point what happens. Okay. So I know I'm going a bit slow, but this is just to bring everyone on the same page. Just to give you an intro of this concept, and then I can build more on this. Okay. So that is what we'll do. So let's discuss at boundary points. Okay. So local maxima and local minima at boundary points. So maybe I'll just simply write on this local maxima and local minima. So maybe first let me discuss what is this local maxima, but this is at boundary point. Okay. So for boundary point, the definition changes. Okay. So now what is the definition at boundary point? So again, I think all these things are there in your lecture again, but I'm just giving you more examples so that you can understand this better. Okay. So here again, f of c, if it is local maxima, c has to be greater than or equals to f of x. But what is that interval? That is something interesting. So this is for all x, which belongs to what? C minus h to c or x belonging to c comma c plus h. So this is the definition for, and the rest you can say that yes, the c is in its domain and f is a real valued function and h has to be greater than 0. So that all things we can write, but this is the main definition, right? So what does it say? F of c has to be greater than or equal to f of x for all x in this interval or this interval. It's not and, it's or, right? So let us look at this part, right? So now if I have to look into this part, so let me say this is my curve, okay, and this is one of my boundary point. You can understand there are two boundary points over here, right? So let's say this is my boundary point. Fine. So what is my interval over here? So if this is my c, then what condition do I have? Do I have c minus h in this particular function?
C
In its
plus
domain?
So
C
So
plus
I'll be looking for this.
it would
I
be
will not
C
be
plus
looking for
H.
this one, right? That is why this or condition is there. So in this particular definition, if I have to look for local maxima condition, then I'll be doing this part, not this, right? It's just that it's not in the domain. C minus h cannot be in the domain, isn't it? So if this is my boundary point, so I'll be using this part to check whether this part, in the sense this interval, okay, this interval, okay, so this interval I'll be using it. So okay, now let's look at this part. In this interval, when I say, what do we really mean? So if this is h, so this is going to be c plus h, right? So what does it say? If I'm using this interval for this particular graph, then I can say that, let's say this is example 1, and I don't think so we have more example here to discuss. So we have 2 example, and I think we can exploit this. Now look at this thing. So having known that this is the one, so what is f of c value over here? So let's say some value, okay, so let's call this as, or just we can just understand with the graph, is f of c greater than f of c, okay, so if this is f of c, and then you know that this is going to be f of c plus h, right? So is my f of c greater than or equals to f of c plus h?
Yes.
Yes, greater
Or
than.
if I take any interval between this, is my f of c greater than
Yes, sir.
f
Yes,
of
sir.
c plus h? For
Yes,
any
sir.
particular interval what I take, this is what going to happen, right? Now you see that this is very this graph is very you know, the way I drew it, I can say that okay, this is what happening. But let's say this graph was something like this, okay. Can I still say that this definition holds true?
No.
No, no.
This is
No.
where we go wrong.
No.
The definition still holds true. It again depends, holds true in the sense, what is my interval, right? So in this particular interval where my h is confined till this, let's say if this is what my h, I mean, this is what my interval is. If I fix my interval, so in this interval, is this a local maxima?
Yes, sir.
Yes.
So what I am paying attention to is interval. When I say, let's say if this was from 5 to 10, in this interval, can I claim that this is my local maximum?
No.
Oh, sir.
I cannot
No,
claim
sir.
at that point, right? So pay attention for the interval, right? Now, having known this part, now let's again discuss at this point, okay? So now what is happening at this point? So for this, if I'm using this point to check my local maxima definition, which interval should I be using, this or this?
C minus H.
So if this is C,
Ending point,
can I
right?
have
Ah,
C plus H in the same, in its
no,
domain? I cannot have
no,
it.
it's
So I
not
can
domain.
just
C
use
minus
this.
H is a domain.
Right. So having known that, now look at C that. Now f of C is greater than or equals to f of C minus H for all H, right? For all H in this interval, smaller interval, can I say that? The answer is yes, I can say that, right?
Sir, can you please repeat once that one?
So it's basically, essentially, I'm repeating the same definition. So you see this, of f of C minus H. So basically, f of C is greater than or equal to f
Yes,
of C
yes,
minus H.
C minus H is greater than C H.
C minus H. So this is
Ah,
happening for
yes.
all the values, right?
Yes.
Or let's say my H is something, it's fixed. Okay, so I'm just fixing my interval, like, okay, this is what your interval is. So in this particular interval, can I say that this is holding true? The answer is yes.
Yes.
I can say that at this point of time,
Holding
yes,
true.
this is going to be my local maxima. Okay, so now understand this. But can I say this as a global maxima or an absolute maxima? Which is global maxima and absolute maxima? Can I say that? Which one is that? Maybe I can use C1 and C2.
Yeah. C2 is global maxima, sir.
So C2 is a global maxima here. Or you can
And
say
by
this is
seeing
absolute
the
maxima.
graph, but how could we see that with the data also?
But here I did not give you any data. If we have any data, if I have any function, you can actually say that. So you see, how do you understand when the function is given? One thing is if you can visualize the function, it's done, right? So one thing is that. Second thing is mathematically solving it, substituting the values in what interval they are saying it, and understanding that, okay, where all it can have the other values, like find out the critical points, right? So it's a big problem again. So let's say if I give you a polynomial of some degree 11, and then you draw a polynomial, then you have so many critical points, isn't it? You have so many critical points. So then you'll have to check at each point that what is the value, right? And after finding the value at each point, then you will come to a conclusion which is giving you the maximum value. The one which is giving you maximum value will that, I mean, that will be the global maximum. But again, there you will have to check at boundary. But again, the boundary does not exist if the domain is R, right?
Okay. Okay.
But again, you at that point you cannot say that yes, this is my global maxima, because that is always going to happen at infinity, isn't it?
Yes.
So you will restrict yourself to the local minima. Well, I hope you understood what is this boundary point. Likewise, how do you get the local minima? So you get local minima with this
Sir,
definition.
excuse me, just interrupting of you. Then if the polynomial is, this is the polynomial and the domain is R, then there is no global maxima minima, only local maxima minima.
You can say that.
Okay.
You cannot claim always, no, because you see, whenever you say that this is my global maxima, the third person can always say that, okay, then what is the value at this, right? So you always contradict that. So you cannot claim that on certain that this is the one. But that's why there is always this interval we fix. You know, we say that in this particular interval, what is the thing? But when we give the interval, then you have to check the value at interval as well, right? So that
then
also
when the
happens.
range is giving, then only we say that this is global.
So you can do the similar definition check for this particular question for local minima. Okay. So for local minima, what we have to make sure f of c is lesser than or equals to f of x. The rest interval are same. Okay. I hope you don't have any doubt here. So we can just move to the other point, like critical points.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Let's discuss what are critical points. So these are concept 3. So maybe I can say this as critical points. So I'll just discuss these three concepts. So this is my third concept, and then I can discuss one problem just to check how much you know this. Okay, whether you understood this or not. Okay, then we can switch to the next topic. So what is this critical point? So let's discuss this. So there are three conditions. So maybe I'll just write them all here. Okay, so that even you can jot it down, and there are nothing more than that. Okay, so you can say that a point C is called a critical point. Maybe you can write, or howsoever. So a point C, I hope when I say C is a real valued function and it is in domain. Okay, so this is always like that. So a point C is called a critical point. Maybe I can write this as CP. A critical point of a function f of x. When do you say this? So first condition, if either, or maybe I can say if f is not differentiable. If f is not differentiable at C, when can we have this condition? When can we have this condition? Can anybody think?
Graph
this?
is not continuous at that point.
Yeah. So those can also be a critical point. Okay. So that is something maybe I can just draw the graph as well so that you can understand this. Okay. So if this is my graph at, let's say, this 5, when C is equals to 5, at C equals to 5, this is not differentiable. So I can say that this is a critical point.
Okay.
Understood?
Yes, got it.
So maybe I can just keep drawing the graph so that you can understand. So there is an OR. Okay, so it's not and. I hope you understand that. or f dash of c is equals to 0. I don't know you understood this or not. It means what? What do? You find the derivative of this?
Tangent is 0.
Slope is 0.
Slope is 0. And when will
Parallel
slope be
to
0?
x-axis.
When will the slope be 0?
Parallel to
critical-
x-axis.
When
No,
there
that
is a
is fine.
turning point.
No curve. There's
When
no
there
curve.
is a turning point, yes.
Turning
So-
point, yeah.
Yeah, so when there is a turning point, so you see this, let's say a polynomial graph, something like this. Okay, so add all these turning points. Maybe it did not go this smooth, but yeah, this is what. So this is C1, this is C2. So though it looks flat, but it is not. Okay, so this is what like curve. This is C3, this is C4, this is C5. Okay, so all these C1, C2, C3, C4, C5 are critical points. So how many critical points do we have? 1, 2, 3, 4, 5. So I can just write down for this particular example, critical point is 5. Right? I hope you understood. So point is this C1, C2, C3, C4, this X values, right? You understood this, right? So now let's go to the third point. When can other happen, at what all places, right? So saddle points are also critical points. So now what do we mean by saddle points? Saddle points are also critical points. Now what do we really mean by saddle points? Basically the second derivative test is unconclusive. You cannot make any conclusion out of it. Okay, so for an example, maybe we can take one example. Let's take or maybe I can take this example. I think you know this, most of you. So let's say f of x is equals to x cubed. So what does f of x gives you? Sorry, f dash of x gives you 2x cube. Sorry, 2x square. Sorry, 3x square.
3x square.
3x square. Yeah.
So now I equate to 0, right? So what do I get? X from here, I get x equals to 0. When I do the double derivative test of this, f double dash of x, what do I get again?
6x.
6x. And when I substitute this 0, so it gives me what?
Again
So when-
0.
0.
when this double derivative test gives me 0, I cannot make any conclusion out of it, because when f double dash of x is lesser than 0, then I can say that this is a point, this is a local minima point, or sorry, a local maxima point, right? That's what we say, no? Are you with me?
Yes, sir. Yes,
Last
sir.
line, I'm not able
Last
to
line.
see it.
When do you say okay, maybe I can just write it down here itself so that I don't have to say that, when f double dash of x is lesser than 0, so, or f double dash, so can I say, what can you talk about C? Is
Local
C a local?
maximum.
C is what? Local maxima. C is a point of local maxima, right? So C is point of local
Maxima.
maxima, and when f double derivative test, this gives me greater than 0, then C is the
Positive, then we
point
can
of
say
local minima,
local minimum.
right? This is a point of local minima. And when f double derivative test of C gives you 0, then you cannot make any conclusion whether that C is a point of local maxima or a local minima. That point is called as a saddle point, right? Because you see in this particular example, this is here at 0, at x equals to 0 is giving me a saddle point. I cannot make any conclusion that whether this is a point. Can look at the graph. Can you say this is a point of minima or maxima?
No, sir.
At 0, you cannot say anything, right? So this is no. Now again, you can tell me, what about this then? Why can't you say at any other point, right?
So what happens when we have a range, sir, for this one, for f of x equal to x cube?
Let's say this is my range.
Okay.
What can you say about that?
No, we can't conclude.
Can't conclude anything. So in that particular, of course, you cannot say at any places, right? Because you see over here, the value, what is happening to the value? It's actually increasing, and it's increasing throughout, right? Cannot say anything at any at this point at x equals to. What essentially I meant to say is, when you do the double derivative test of that particular function, and if it gives you 0, so that turns out to be a saddle point. Or we also, whenever if there is a graph, we can mention that yes, this is a saddle point. Okay. So this is the third condition. So now where all we can think of a critical points? At boundary points also, can we say something? Because that is also a gray area, isn't it? So what happens at boundary points? So this is, you have to make a note of it. Okay, boundary points are not critical points. So make a note of this. Okay, boundary points are not critical points. Now the next question is, can you differentiate a boundary point? Can you differentiate at a boundary? So those are some deep questions, so no worries, I'll come to that slowly. So but this is something you have to make a note of it, that boundary points are not critical points, and for a function to be a critical point, these are only three conditions. First is, a function should not be differentiable at C. If that is happening, then I can say that yes, that is a critical point. Secondly, the first derivative test of C gives me, when you equate to 0, and then you find out that that f dash of, or maybe that is what you do, right? So you take the second derivative test just to check whether that is a point of maxima or a minima, right? So that is what you do, and from here this C is again a critical point. So wherever there is a turning point, so maybe I can just give you here in the bracket that at turning points, that is going to be a critical point, right? And the saddle points are also what? A critical point. Saddle points are those where the second derivative test is 0, so you cannot conclude anything about that particular point, so that's why you call that as a saddle point, and you can say that that is also a critical point. So these are the only three conditions, and at boundary, make a note of this, boundary points are not a critical points. Now, having known these many things, let's discuss one problem. Okay, so also before going to that, let's discuss before going to a main problem, I want some concept to be cleared here. Maybe I can just say this is a conceptual problem, and you can just make a note of this. Okay, it is something you don't know, that is something I know, or maybe we can, as per our knowledge, whatever we have studied in these particular 2 weeks, we cannot say anything about it. So let's keep one stance for this particular course throughout. Okay, so if this is my function, okay, so this is my function, let's say this is my x-axis, this is my y-axis. Okay, so over here, now you understand, right, what does this symbol indicates? That this point is included over here, this point is not included. Okay,
Yes.
so now if you understand, right, all of you?
Yes, sir.
Okay,
Yes, sir.
yes. So now let's talk about this. At this particular point, what is happening? The point means you understand, this is what I mean, right? So this is some values and some value exist over here. So over here, let me write down three things. The limit exists at this point. Limit exists at this point. I will say yes. And what you will be, can you check left hand limit for this?
No, sir.
So you can't say anything about,
Because it's endpoint.
so you can't say anything about left hand limit. So if you have to find out the limit, just do the right hand limit. Essentially, this is what it means, right? Okay. Is this continuous at this point?
No, sir.
No, sir.
No,
Because-
it is continuous. That is something you can make a note of it.
It's
Because you
continuous.
see the limit value is same as functional value. You understand, right?
Yes, sir.
Okay. Is this differentiable over here? Again, can't say
I
anything about
can
this.
can't say anything.
So maybe you can just circle this. It's not correct to say that this is differentiable. So you cannot say anything about whether it is differentiable or not. Okay. As per our knowledge, whatever we have, you require more mathematical knowledge to tell whether it is differentiable at this point of time. Because there are so many scientists who can say, no, this is differentiable. There are so many mathematicians who can say that, no, it is differentiable. So this is a controversial thing. So we can, just to be on the safer side, that we can't say anything about it. Okay. So just keep it with you. Can't say anything about it. I hope you understand this. This much is clear. Okay. So now see again, I'm taking you back to here. Note, boundary points are not critical points. This is a boundary point. Is this a critical point?
No, sir.
This is
No,
not a
sir.
critical point. So make a note of this, okay? Because we will tend to do mistake in our exams if we have a question like this. Okay, now come to this part. Do limit exist for this?
No, sir.
No, sir.
Here we go wrong. I don't know how many times. we
LHS.
get-
LHS.
Limit exists. Yes, sir.
Limit
This is,
exists, yes.
limit
Can't
exists.
say about RHS, sir.
Ah,
You can't say anything about RHS.
limit exists. Yes.
Anybody still thinking why they are saying the limit exists?
Yeah, its endpoint we have to check only for left hand limit.
No, that's not the thing. It's basically, see, what we do mistake is we see that here in limit you tends to that particular value, right?
Right, sir.
Yes,
Right,
the
sir.
tends to.
Right? You
Right,
tends
right,
to,
right.
right?
Hmm.
Is this continuous?
No.
No, sir.
So now we are going right. So basically it is not continuous. Why? Because the functional value
Function
is not,
value is not there.
it's
yeah.
not given. Yeah. So you
That's
cannot
what I'm thinking when you ask limit
so when
exist
I
or
asked
not.
limit, yeah, that's why I told. This is what we make mistake always. Because
Yes, sir.
there is a very slight difference between this limit and continuity.
Right, sir. Right, sir.
So can you say anything about differentiable?
Not
say.
possible, I think.
Can't say anything about.
Can't say anything.
So, but it is not continuous, so it can't be differentiable.
Of course you can say that. Or yes. That's a valid thing. It's not differentiable here. You can't say
Yes,
just like
this is
this
not
here.
continuous.
It is not differentiable. This is the right thing to write. Thank you. So it is not differentiable just because it is not continuous, right? So not differentiable, or I can say that maybe I can just say differentiable. So the answer is no. Over here it is circular. It's just that we cannot make any conclusion over here, but over here we can rightly say that this is not differentiable, right? I hope this is okay to all of us.
Yes,
Sir,
sir.
one basic question, that is for the first point, how it is a continuous, because when you continuous, it has to be left limit equal to right limit.
Okay, so you understood that limit exists at this?
Yes, that thing I understood, but the second point I didn't.
Wait. So if you understand that limit, second point in the sense continuity point.
Yes, continuity point.
Okay.
How is it point?
Can you tell me what is the
Continuity at this
definition for
point?
continuity? What are the two conditions?
And that
for
the
continuity?
limit exists and both limits will be equal. Left hand limit.
No. When both limits are equal, then you say that the limit exists, right?
Yes.
So when you say, you cannot say the limit exists, then both the limits should be there. You cannot
Okay,
say that.
I'm confused.
Okay. So you first understand that limit exists for this, and we only check left hand limit at boundary points. Okay.
Yes.
Oh, sorry. I mean, you either check left hand limit or right hand.
Or right hand limit. One. That's I get it.
So that is one thing. Once you find out, you say that, okay, the limit exists. What is the second definition or the second part of continuity definition? That the functional value should be equals to limit value.
Yes. Yeah.
Over here, you can find the functional value, but over here, you cannot find the functional value because it is
right.
It is not given.
It is not given. Okay.
Right?
Okay. Now I get it.
You get it? All right. So now let's discuss one problem. This is again like a conceptual problem, not conceptual, but now I think you can give the answer to what I write here. Okay. So now let me just give a question on this. So maybe I can just draw some big diagram or something, or we can try to solve that particular question. Okay. So now we also have very less time. So we'll try to cover more questions. I'm sorry. So here I have a function, something like this. So this will cover all our concept what we have discussed till now. Okay. So let's draw something. Maybe a curve like this. Goes down. And there is something like this. Okay. And let's say I have some condition like this. this is that. Okay, assume this is a straight line, okay? Fine. So here, this is what I have. So I can just extend this further and call this as y-axis. All right. So now this is something, let's say 6 comma, maybe I can say 4.5 or something. So this is what its value is. So you understand when I write 6 comma 4.5.
Yes.
Okay, likewise, I can just say something more about this. So this is like 5 comma, let's say 1.5. Okay. This is somewhere like, okay, maybe I can just extend this further and take it down till here and make this. Okay. And this is, let's say this is -1, like at least at -1 you see this, and this is some roughly, it's not the exact value, 0.5, and let's say this is another, maybe I can say 3 comma, maybe I can give it as 1, 3 comma 1. Okay, so now these are certain things which I have given here. And yes, this point, I'm saying that this is a saddle point. Okay, now question is, now I have some questions over here. So maybe I can say Q1, I can just simply write down here. How many critical points are there from -1 to how many? So you can understand from here, what is the domain for this particular function? If this is my function f of x, what is the domain of this particular function? Can you say me?
Domain, point near about 0.5 is open. A domain.
-1.
-1
Sorry,
to
I thought
1.
range. Okay, -1 to 6.
6.
Yeah, you were finding range at that time, is it?
Yeah, sir.
Yes.
Okay.
Sorry.
Fine. So this is the domain, right? So you understand -6 is not included and 6 is included. So this is my domain, right? Okay. And range is something else. So again, we can talk about something range over here as well. So maybe I can just say something range is somewhat like roughly
0.5
0.5.
to
This is wrong to
4.5.
write, but I cannot actually claim that, that this
Yes,
is what. So maybe
nearby.
and maybe I should also not say this, but again, I can claim that, yes, this is not included. But again, I can say that, yes, roughly from 0.5 to, or maybe I can say that 0.5 is not included.
Yeah.
Yes, 0.5 is not
included, and
4.5.
to
6
4.5.
is
But
4.5 is
again,
included.
it is wrong to write this also, but let me say that, okay, fine, this is what it is for trivial understanding, just for understanding some other concepts. Okay, so question 1 is, in its domain, how many critical points are there?
We can take the turning points, right?
7.
5, sir. 5.
7.
6. 6, sir.
4.
Okay.
5.
5.
Yeah.
7.
I
7.
think so, 5, sir.
So 6
Because-
including saddle point.
How many?
I think it is 6 including the saddle point.
6 including the saddle point. Okay, let's see this. Okay, first of all, I cannot say
8.
anything about boundary,
6,
so I'll
6,
just leave that.
6,
8.
6.
6. Okay, so
6,
let's see.
sir.
Let's see that. Okay, so this is one critical point. All of you agree?
Yes, sir.
Agree?
Yes, sir. This is critical point.
So 1, 2,
And saddle point and the
3.
down. See.
This is another 4.
But the boundary point is not critical point.
But these are the boundary points. These are the boundary points, right? This is not a boundary point. This is the part of function.
Okay.
Right? So 1, 2, 3, 4, 5, 6, 7. How many do we have?
7.
Understood?
Yeah, I thought that this point is.
No, boundary points are the end points. So that's why we call that as a boundary points.
Okay, the function is continuous from that point. That's why we are saying this is not a boundary point.
That is a
Okay.
continuous function.
Okay,
I mean,
got it.
there is some functional value over there, right?
Yes.
Just say it's not continuous at that point,
But
but the function is
huh.
defined. The
Yeah.
function is defined for that point.
Yes.
Okay. So now
Now
we
I got it.
understood that what this is, right? So do you have any doubt here? How to calculate the number of critical points?
No, sir.
So this particular thing which I'm discussing you, this was asked in the end-term exam. And this is one of the blue colored questions. So blue colored questions is the top 10% top 10% scorer in maths made mistake in this. You understood, right? So the top 10% scorer in mathematics, let's say they have really good marks, but they made mistake for this particular question. So you pay attention for this. That is where we understood that, yes, this is where you are going conceptually, they would have gone wrong or something. So it's fine. That's not a problem. Thereafter, we thought like, okay, we can discuss this concept so that, you will not have difficulty here. Okay. So now question 2 over here. Find the number of points where f of x has local minima in this. Okay, maybe I can just write this down. Okay. Find the number of points. This is, pay attention to this. Find the number of points where f of x has. So of course, this exactly question was not asked in the end term. Like I have, this part was there, this corner thing was there. So I just try to mimic that kind of question over here so that, because we have all the things what we can discuss, right? That is why this question will be helpful to understand all that. So find the number of points where f of x has local minima in -6 to 6, sorry, -1 to 6. So could you tell me how many point of local minima do you have over here?
3.
Answer the 3. I have a question. In the saddle point, is this maxima or minima? What the thing is happening?
You should tell me that. When do you say a saddle point?
Okay, it's going down.
No, you think of second derivative test. What is the saddle
Okay,
point?
but how do you find the second derivative test?
No, but when do you say that saddle point exists?
The saddle point thing is a little bit.
When the function, when f double dash of c is 0.
Okay.
So when does
Okay.
that happen? So it's when it is not a point of local maxima or when it is not a point of local minima.
Okay.
Right?
Got it.
Right. So saddle point is neither, isn't it? So okay. So how many do we have here?
3.
3, sir.
3.
Yes, sir.
Which all? Maybe I should use different color. I'll use red here. So which are local minima points, right? So this is 1.
Yes, sir.
1. I can say this 3.
Yes.
I can say sorry, second and 3. Look at this part. Can this be a local minima? No, it's just because you see this. Look at the graph over here. What is
Which
your
part,
f of
sir?
this part? Let's
Yes.
say this is something like 2, right? So you see this f of 2 is actually, it has to be f of 2. Okay, fine, I get it. Now where I should catch you. So maybe I'll just ask you the next question and you can give me similar question in its domain, but you're finding what? Local maxima. Just tell me how many points do we have for local maxima?
Sir, one question on local minima.
Mhm.
So when you say that a 3, right, at x is equal to 3, but there would be some point which is less than the value f of x at x is equal to minus 0.5 or 0.8, right?
0.5? I didn't get you.
The leftmost corner, right? We are not including -1. but there might be some point like minus 0.8 or 0.9, which is less than this 3, right? F of x value.
In this interval you're talking about?
Yes, minus 1 to 6. Yes.
Minus 1 to 6. No, you're not taking, see, when you talk about local maxima and local minima, those are local phenomena. You don't take entire domain at that time. You just
Okay.
take the local part of it.
But how
It's-
do we define the range, sir? The local part is how do we say that?
What do I mean is this definition is a local property. Like for an example, the tangent is a local property. Right? You understand, right? How do you find you find a tangent in that small interval, right? You don't
Yeah.
take the entire domain and check, isn't it?
Okay.
You understand? What do I mean by this? Do you have doubt in this? Should I give you a counter example so that you can understand?
Yes, sir. Because you have mentioned 3 points in local minima, right? So I just want to comprehend how we determine
Yeah.
the local points.
Right. So what I mean to say is, whenever you say this local minima or local maxima, these are a small interval properties. This is not on entire domain. For an example, what is the definition of let's say a tangent or a slope? Basically, what is the definition for a slope or a tangent line? Basically,
Okay, a straight line at that point, sir, where we are.
A point.
Anybody
of a
just tell me anything like
line, how the graph will act at that point, means whether it will rise up or down.
so when do you say that? What do you really mean by tangent?
Linear approximation of graph at that point.
Okay, no, that is the different thing. Well, that's the tangent line.
Yeah. It's like a secant, but when you
What did we studied in our school, normal school days? It's basically a tangent is a line which just touches the graph, right? It just touches the graph. This is what we learned, no? In our school days, teacher used to draw a circle and then used to say, okay, what is a tangent? A line which just touches the curve, right?
In circle, there are infinite many tangents can be possible.
Right. Agree. It's happened for any other things. But now look at this. When we say that tangent, so tangent is basically a local phenomena. Now, when we say in our school days, we used to study this, right? So tangent is a line which just touches the curve, right? So if I have this curve, I just touches in the sense, this is what, right? The tangent line cannot be this.
Okay. Yes.
Right? It is touching at two different places. I mean, it's basically crossing at two different places. It's not even touching it. So what do you mean by tangent line? So now you understand this. Okay. And we also learned that tangent line is very unique, right?
Yes.
Did we learn that? Now look at this sine function. This is one, this one. So you know that sine function, right? So this is what sine function, right? Now look at this tangent line over here. This is what will happen, right? This is a tangent line. Is this touching at two different places? Is this touching at two different places? You know sine function, right?
Yes, sir. It will touch. Yeah, it will touch.
It will touch at many places, right? So again, so tangent line is not unique in that point, right? If you take the entire domain, you're understanding. So what I'm trying to make you understand here is basically what we studied in our school days, that tangent is a line which just touches the graph. That is correct. But there should be one more thing that we should add, that happens in a small neighborhood, that happens in a small interval. So when I say this sine function also, that if this is my sine function, and when I say find the tangent at this point, what you essentially do is you take a very small interval and then you find the tangent at this. Basically, in this small interval, this tangent line should just touch a single point, a very single point. But when is that happening? In this small interval. You do not take this entire domain and then you check the tangent.
Okay.
So what do we really mean by that is, so just to reiterate this, a tangent is a line which just touches the graph in a small neighborhood. That happens in a small neighborhood. So when I say that small neighborhood, so it is what? It is a local property. So a tangent is a local property. Okay.
Yes.
Likewise, when I say this, local maxima and local minima, this is again a local property phenomena.
Okay.
Okay.
Yeah.
So now you should be able to comprehend this. Okay.
Yes, sir. Yes.
So, yeah. All right. So now tell me for this question 3, I mean, for this sub question number 3, how many local maxima do we have?
2, sir.
3.
2, 3. Okay. Any more answers?
1.
This one.
2, sir.
Okay. Let's see that. So maybe I'll use different color here. I need answer with confidence.
4, sir.
4.
Confused.
Confusing, but we'll learn so many things. We are spending a lot of time from that time, you know, we are discussing this.
So
It's
3.
like
It's
a-
a total new thing, so trying to comprehend.
Okay, but you need to be fast now. So over here, local maxima, let's discuss how many. Can I say this is local maxima? Just look at the small interval. In this small interval, this is my maximum value. So yes,
Yes.
this is my local maxima. I can say that yes, this is a local
1,
maxima.
2, 3, 4.
I cannot say anything about saddle point, so forget about this. This cannot be my local maxima because this is my local minima. We'll come to this in a while. This cannot be again a local maxima. Can this be my local maxima?
Yes.
Yeah.
Yes. Can this be my local maxima?
Yes.
This one. At 5. Is this a local maxima?
No, no, no.
No, no, sir.
No, sir.
Minimum.
Or this
This is
is?
minima.
Yeah.
Can anyone say, I mean, is this a local maxima? Any of you claiming yes?
No. Don't think.
If yes, I can just discuss again. If not, then I'll just move ahead.
Which
No,
point?
sir, I don't think.
This one. Is this a local
No,
maxima?
sir.
No, 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 sir.
No, sir.
Okay, so all of you are fine till here. Is this a
Yes,
local
sir.
maxima?
Yes, sir.
Sir.
Yes. Local maxima at boundary point.
Yes. This is local
See, a
maxima.
global maxima or global minima is also a local maxima and a local minima. Understand this? Okay. So these 3 are there for sure. Now look at the saddle point. Sorry, not saddle point, but this breakage place where this something is happening, right?
Yes, sir.
We
This
discussed some
point.
example if you remember. When something comes like this, just go with the definition. What does it say? F of c should be greater than or equal to f of x, and you know that what? In what interval? X minus h and
C.
sorry, I should take c minus h and c plus h. In this interval that this has to happen. When I take c minus h, is my f of c greater? This is my c minus h, right?
Yes.
Yes.
SFC.
Is my f of c greater than c minus f of c minus h?
Yes, sir. It's great.
Yes, sir.
Yes,
It's
it is greater.
greater.
Is this greater than f of c plus h? C plus h
Oh.
is somewhere here.
No.
Yes. Okay.
It's
Yes.
greater.
Yes, C plus H is going. That's why I'm counting this point. That's why I'm telling you 4.
Yeah.
I'm not confident enough.
Okay, fine. I don't know. I'll just repeat this again because I can feel still hesitation in you. This is my C minus H. So when I am checking whether this is a point of maxima or not, what should I do is I should check these two conditions. F of C has to be greater than or equal to F of C minus H, and there is a and, not or. Okay, so F of C should be greater than or equal to F of C plus H.
C plus H.
Okay. Over here we understood when it is C minus H, this is the maximum value for me. When I take, I mean C minus H when I take, so when I take any C minus H value in this small neighborhood, F of C is greater. Agree? Agree?
Yes, sir.
Yes.
Or is it I'm using some complicated term?
Yes,
If you
yes.
just tell me, I'll just try to, you know, explain you in much easier way, or maybe
Yes.
also. Now look at this. When I take F of C plus H, C plus H is what? Now this is my C. C plus H is some this value. But what is my F of C? This is my F of C. Is my F of C greater than or equal to F of C plus H?
Yes.
All of you?
Yes, sir.
Any doubt over here?
Here FC is greater than FC minus H and C plus H.
Okay,
So
no, I'm
this is the
asking all
point.
those who are not responding. I mean, tell me, you can understand this?
Yes, sir.
Sir, there is a discontinuity, that's why it is happening, right?
Okay, no problem. So if you have doubts, you can just rewatch this video. I mean, this is kind of important, just for all of you. You see, I have discussed some examples over here, this breakage of things. You can go check this. And I think I have done it extensively. You can just go check it out, but do not worry with
Actually,
this breakage thing. It's okay.
I
It's
joined.
okay.
we were
Oh, you joined
discussing
late,
that.
but do watch this. I mean, do watch this again. You should be able to understand this. Because I
Okay.
have discussed so many places where we made mistakes, or like your seniors in BSc degree program who have made mistakes, and that kind of questions, or like similar kind of questions, I have tried to mimic so that you don't make questions, and so that we can make different questions, not repeat the same question. Okay. So that's how we both evolve, right? So yes, so you understand, right? So how many local maxima do we have?
Sir,
4.
4.
4. Then this is also a local maxima. So now we understood. Okay.
Yes.
Can you tell me what is global maxima? Okay. Can you tell me
Sir,
what is global minima?
Sir, both point is considered for local maxima. Here.
There is one point, and the point is this. There is only one point. This is the point where I'm checking. Let's say this is some value, let's say 2. This is where I'm checking. Right? What is the value at 2? The value at 2 is this one, not this.
Upper
right?
point.
Right? You understand, no?
Got it.
So can you tell me what is global minima?
3,1.
3,1.
Maybe I can say
It
global
does
minima
not
value
exist.
does not exist. That
Yes,
is the
ma'am.
right to say. It does not exist. Right? Because you can always claim, if somebody says, yeah, it is 0.5. You cannot say roughly 0.5. That's nothing, something like that. Okay. It is just to give you a pictorial.
The
some
point is
values.
not given. That's why it's not taken.
Just to give you a pictorial answer. That is why I gave it. Okay. That is something roughly 0.5. Just to give you an idea that, this is the lowest value. I mean, it is tending to lowest value. That is what I meant to say. Okay. Okay. Sometimes even in exam, we might give you the lowest value is 1. And believe me, there were more than 50% students who actually gave this answer as 1. They did not consider this, but they told that, okay, I would have heard that, yes, the value does not exist here. The local minima value will be 1. That is what they made conclusion. But that is not right, because you see, there is other value, right? You can also claim 0.9, isn't it? You can also claim 0.8, 0.7, 0.4, I mean, 0.6, right? You can also claim that. But so many students made mistake over here saying that, yes, the one is a local minima value.
It's a local one.
Sorry, global minima value.
Yeah.
So you understand this. So though you are answering it here, but when it comes to exam, you yourself will make mistake. And why is that? Because you don't know, when you have that pressure, how do you handle that pressure at that point of time, and how your mind should work. That can only happen when you are doing a lot of practice. You understand that?
Yes, sir.
And that is something we should learn. Like, when we have a pressure, then how should we tackle a problem? That is something very much essential. Because let's say when you're going to later on, when you're going to work for a company, or let's say something else, or anywhere else, it's not going to be this easy. Like, I'm teaching you and you are listening, right? You will always be in pressure, and you will feel that, okay, now if this is the pressure, then how do I handle this pressure? So this is something you will learn essentially. Like, when you're solving this, when you sit for the exam, and then you have a question, and then you tackle the question, then you have this, then yes, you are actually evolving for a something, or basically you are being a problem solver, right, at that moment, right, or for that situation, or maybe at that condition, or when you have that much burden and something. So I hope you understand that. So the best thing is practice. Okay, so now let's discuss this. Now I think this is fine. You can tell me this value. Now what about, what is a global, look at the word global maxima value.
6.
6.6. That we
6.6.
can, for sure we can say that.
Yeah.
Right. Okay. So now we discussed more about this critical points and all that, right?
Global maximum is 4.5.
I have a question.
We define that it is a global minimum or
Okay.
maximum.
Just give me a minute. Just give me a minute. I'll just connect my charger. Just give me a minute. Okay, fine. So yeah, some of you were asking something, some doubts and something.
According to the algebraic way, we have to just substitute the critical point and then find the value. But
Yes.
according to the graphical way, as I can see in that graph also, we told that 3 is that local minima and 6 is maxima. How can we define that it is global maxima? Means should we consider endpoint as local maxima or what?
That's what, like, you'll have to check at each and every places. Now, for an example, if I had to tell you, this is the question, and wait. This is a function, okay?
Okay.
It's some polynomial function. How many degrees do we have? X, this, and this. So 1, 2, 3, 4, 5. Maybe I can say these are my roots. 1, 2, 3, 4, 5. Let's say this function is f of x is equals to. So I'm giving you a function, and then I'm telling you, okay, find the local minima or local maximum. And I say the function is x minus 1, x minus 2, x minus 3, x minus 4, x minus 5. This is the function I gave you. Okay. Now I'll tell you, find out the point where it is, which has a local maxima and the global maxima and a global minima. Okay. And I also say that this function is defined from this domain. Let's say from 0, let's say this is
5,
7, 0, 7 to R. So what is the domain for this function? This is my domain. 0 to 7 is my domain, right?
Yeah.
So I am restricting my domain over here, right? So how do you solve this particular question? You will solve it in a way that you first differentiate this function, right?
Yes.
Then you will find out these critical points. You will get this value. You will find the values at this. So you will get some x values, right? When you do the first derivative test, you get some x values. So at these x values, you will substitute that x and you will check, okay, what is the value you are getting at that, right? So at how many places you will be checking? 1, 2. At this also you will check what is the value. At this also, at 3, 3, 4. So from this first derivative, you got at 4 places that you have to check the values.
Yes.
And you will find some of the values are giving you some, I mean, some of the points are giving you the maximum value. That's fine. But you will also check at this boundary places. What is f of 7 and what is this f of 0? What is this value giving me? Okay, so on overall, whichever is giving you the maximum value, that is your global maxima, and whichever is giving you the minimum value, that is your local minima or global minima.
Why we will consider this global means endpoint? Why should we consider this endpoint? It means, according to what I can see, it is not having any turning points or anything. So how can we say? Maybe the graph could move up also, or it could move down also.
That's what I made it. I restricted it. I'm saying that you cannot move more than this. You will only be till here with this domain. I'm saying, right? Now, if you come and claim me that, yeah, this is my maximum value, can the third person cannot say, if, okay, this is giving you some values. Let's say this is 3.5, 8. What could be the value over here? 7, is it going to be 8 or what? Something more than that.
Be much higher than 8.
Much higher than that. Maybe it will be like 12. So can you claim that this is my maximum value? Can you say that this is my global maxima? You cannot say, right?
7, 12
So
is
what you will do? Yeah. So basically, your global maxima value is going to be something 12.
So out of all the values, the value which has the highest.
Right. So what do? You substitute the values and get, right? So should I quickly discuss some of the questions on maybe Riemann sum? Should I touch up that?
Sir, I haven't watched
Yes,
that
sir.
lecture.
Yes, sir. It's confusing. Very.
Riemann sum is a bit confusing. Maybe I can just discuss Riemann sum, and then in the next lecture we can see that definite integral and the integral problem. But I just want to give you an idea about what this Riemann sum is and discuss some 3-4 problems on this. Is that okay?
Yes, sir.
So let's discuss. Let's do that. Okay, so let's do some questions on Riemann sum. Maybe that will be good, because that is where we make mistake. Okay, so if we can do some problems on that, then it will be good. So let's discuss some Riemann sum. So basically, to explain you what Riemann sum is, maybe I'll just take a photo of it. This definition is given in your solve with us definition, so I'm just taking it from there. I'll just copy paste it there because it is so much to write. I don't want to waste my time in writing that. So I can just explain you from there the Riemann sum, and then I can take up some of questions, and we can exploit every part of it, whatever is being asked. Okay, so don't worry about it.
Sir, when are the maths mock tests?
That's going to happen on Sunday.
Sunday. Time?
Evening 6 to 8.
Okay.
There will be time mock. This Riemann sum. Okay, maybe I'll just write it down. I'm not able to find it where it is. So,
sir, you can use find.
Control F, sir.
Yeah. You can just find it and write Riemann. It will automatically be there. I think yeah, maybe.
So maybe I'll just take a. So this is this definition, you have it in your solve with us. What do you get, right? That solve with us, you can see that explicitly it's mentioned there. That solve with us, you can solve questions over there, that kind of thing, not that periodic one. Okay, so it's not that one. So you can just go and check this definition. So it's just that I'm taking it from there. Okay, now let's discuss this. So first of all, you have 3-4 components over here, and how is that transition happening, that I can discuss here. Okay, so what do you mean by Riemann integration? So first let me explain you something over here, that so you see this, let's say this is my curve. Okay, and I have to find the area under this curve. Okay, so how do you do that? You first, if you don't know any integration formula, then how do you do this? Area under the curve is what? Maybe from here till here. It's this entire region, right? This entire region. Isn't it? This is what it means, isn't it?
Yeah.
Right?
Yes,
So,
sir.
okay. So now this is our A and this is our B. Okay. So this is what? Essentially f of A. And this is going to be our f of B. Maybe I'll just draw like this kind of curve so that it will be easy to. So this is going to be my f of b, right? So area under this curve is going to be, how do you say that area under this curve? So you say this is my function, let us say this is my f of x. So how do you say is, you say this way. Like I'm just talking normally how we did it in our school days. So this is my function f of x, and now I have to find out the area under the curve. That is from where to where? From a to b. So you take this a, b, right? So now when you do the integration of this, so when you integrate this, so this is not f, yeah, fine, this is f of x dx. So when you integrate this, you do get what is, I mean, when you get, let's say you get this f of, you get some value, so you get some function. Now let's say that function is f of x, and then what do? You substitute this value a b. So what do? You do this f of b minus f of a. So you do what? F of b minus f of a, and whatever the value you get, that gives us the area under the curve, right? So how does that happen, right? So just quickly look over it, right? So now you see this, when I say a and b, and if I have to find out, now I'm just going to the basic. I told you how do we do at advanced level, that yeah, we know the integration formula, substitute it, definite integral and everything, that is fine. Now let's go with the basic definition of it. Like how did this even come into picture, right? How we started this was like, we basically started with taking this rectangle, small rectangles, right? So you take this another rectangle, then you take another rectangle, right? So that's how you drew n number of rectangles, and then you found the area. Likewise, you go till here. Okay, so maybe I can just draw one more rectangle over here. Oh, that's not right. So this is something I get. So we know the formula for finding the area of a rectangle, right? What it is? If this is, let's say if this is, you can just draw it here. This is going to be, this is a, and let's say this is a plus h. So this is a plus h, and let's say this is, yeah, this is going to be f of a. So how do you get this area? F of h plus into f of a. Because this is the height. This is the height and this is the breadth, right? So height into breadth gives us the area of a rectangle. Likewise, you will do for this rectangle, this rectangle, this rectangle, this rectangle, this rectangle, this rectangle, and n rectangle, and then you go with this. So you find the area of this all rectangle, and then you get the area of this curve, right? I hope you understand that much. But we are missing something out here. Now look at this. We are missing out this place, this place, this place. We are not finding the area for this, right? We are not finding, isn't it?
Yes, sir.
Then how do we find the area for this part? One thing we can do is this h which I have taken, I can reduce the width of it. I can say that this is not my h. Now I would say that this is my h. Now what did I do? I drew this h that small that this void is very insignificant. So what am I doing? This h is tending to what? It's tending to 0. Let's say initially I took this h to be somewhat like 2 or something. That is why this kind of rectangle I got. When I say my h is 1, so the a plus 1 will be somewhat half of it. Agree?
Yes, sir.
Yes, sir.
When I'm taking the half of it again. So what? It will become a small, still narrower. Then can I say this void, this area is getting decreasing? I mean, it is becoming smaller and smaller.
Yes, sir.
Right? So what is happening when this h tends to 0, I can find this better area, right? If I say that when I was using this larger h, I was getting, let's say, area something like 9. So I'm actually underestimating it or overestimating it for this particular one. I'm underestimating the area, right? So when my h tends to 0, I can say that, okay, now my area is something like 9.5. when h tends to 0. So this is going to somewhat giving me accurate answer. Or let's say when h was, maybe I can just write down, when h was, let's say, when h was somewhat like 2, then I was getting this area, that integral value I was getting as 9. When I took h as, let's say, something like 1, then I'm getting this area. When I say that my h is tending to 0, it's not going to 0, but it is tending to 0. The moment I make it 0, then I cannot find the area, right? So what I'm saying is it's tending to 0. At that point of time, I see that the area actually tends to what? Somewhat like 10. Let's say this goes to 10. So what essentially is I have to reduce this h. Then how do we do that basically? For this, we will be using some kind of mathematical tool. Okay. So how do we do that? So let's understand this again. Okay. So I'm not erasing this part because I'll be using this again. So you see this here, partition of an interval means what? You see this AB I have drew. Okay. This is fine. This is my A and B. This is my interval. Now next, what are we doing here is maybe I can just read this statement and then explain you. Let AB be an interval. Choose a definite order set of a points, including the endpoints from the interval AB. Let x0, x1, x2, and dash, I mean, blah, blah, till xn, which is in this interval. So what am I doing? I'm just taking this intervals, right? So if this is A, this is, let's say this is my x0 is A, then let's call this as x1, let's call this as x2, x3, x4, and let's say this is my xn is B. You understand this now? What am I doing? I drew this partition. So this is what it means. Partitioning of an interval. My interval was what? AB. Now what am I doing? I'm just separating this. I'm partitioning it. Right? So I have partitioned into x1, x2, x3, and x4 and x4x. So this interval, it may need not be of same size. It might be varying length. But just for simplicity, when you're solving a question, we take a definite interval. We fix the h. This interval, we fix it. Okay, you understand that? But it need not be the same. It can be of different weight. Okay, I'll take up some examples and then explain you. I know when we talk more math, right, it's kind of very difficult to understand until or unless we do problems. But let me just tell you something so that we can have some vague idea, and then I'm explaining it, then I can bring you back here. Okay. So now you see this. From here, what you can take from me is the interval is given AB, and what am I doing over here is this bigger interval I'm breaking into a smaller interval, and this is how I'm breaking. Let's say the next one, that is x1, is actually equals to what? x0 plus h. Likewise, x2 is what? x1 plus h, or some other thing, some other width. If I say like the width is fixed, then I say this. So you're understanding that I drew a different rectangles from here, right? So this is what partitioning of interval it means. Okay. So having known what is partitioning of interval, let's go to Riemann sum. Okay, so now let's say a function f which is defined from this domain D to R. So now this is a domain, and you know this is codomain, right? Basically, and this domain is a subset of R. Okay, suppose this is happening in an interval a comma b is contained in the domain. Now what we are saying, this interval we discussed here, right? This AB. Of course, we can say that this function is going from somewhat like this to like this. Okay, but what am I saying is you find the area from A to B, not an entire function, not in its entirety, but from A to B. This is what it means. That D is basically a subset. So I can just write down that D is a subset of R, but your interval AB is also a subset of this D. Now you can understand this. AB is a subset of your domain. Basically this interval. Now let P be the partition of an interval. Now what is this P? P is a partitioning of this interval, and how is this defined? So partitioning of interval is basically defined over here. You are saying that, okay, you have to take it this many intervals. We are fixing you that you can choose like 5 intervals or 10 intervals or something. In the question, it will be given, okay, you choose 10 intervals, or let's say you choose 5 intervals. And then then what is those values will also be given to you. So don't worry about that. When I'm taking up question, you will understand. And also now understand this from here. Now, if I have to take this x2 minus x1, x2 minus x1 is what from this figure? Can somebody tell me?
H.
H. Because I told you in the very beginning that I'm fixing this h, right? So
Yes.
x2 minus x1 is h. Okay. So now having known this, this is what delta xi means. Xi means one higher value minus one the lesser value. So this is xi minus xi minus 1. Right? So if xi is 2, I is 2, then this is going to be 2 minus 1, which is going to give me 1. Right? So this is what. So how do we give the notation? Delta xi. This is what we mean. So delta xi means nothing but essentially the same thing. Right? So delta xi is basically what is this width. Okay. So we got to know this is basically delta xi. Okay. So understand this. I'll come to this part in a while. Let's first understand what Riemann sum is.
Sir, 1 minute. X2 minus X1 equal to H. How, sir?
I told that this is what the width, this width I'm claiming that this is H and this is fixed. That is how I do.
Okay, basically I H means height.
No problem. So now understand one more thing from here. Let's first, now Riemann sum formula is this one. What is being written over here. This is the main formula. Okay. Now, even if you did not understood what I was explaining you till now, pay attention from here. I'll tell you how to use the formula. Okay. Riemann sum formula is this. Riemann sum formula says what? Summation I to n f of xi times delta xi. Now understand this. You know the area of a triangle, right? Sorry, area of a rectangle.
Yes.
Yes, sir.
This indicates what? Height. Like
Times.
I did it over here, no? This when I did it for this particular rectangle. What did I do? F of a value I took. If I want to find out the area of this rectangle, what should I do? F of a times
H.
h, right?
A.
H. H.
X of X into H.
H. So this is going to be the area of this rectangle. Delta xi is giving me what? The width of this.
Width.
Yes.
So this is nothing but width, right?
We are summing up
So
all
height
the
into width. Height into width gives you what? Area. And this summation tells you what? This width plus this width plus this width plus this width plus so on and so forth till end.
Yes.
So when you do this all, that will give you what? The basically the integral value for that. So this is what the Riemann sum is. That's all. But you know, looking at this definition, we get scared. Okay, what is this written actually? You know, we might get lost in the very beginning. Like, okay, now it's, you know, it's not my cup of tea. It's something we go up like that, right? So do not worry. When you don't understand, still you can go from here. No problem. All you have to understand is this is going to give you height and this is going to give you width. Height into width is nothing but the area of a rectangle. That's all. So this is going to be area of a rectangle. And when I say n, so n area of rectangles. Now you understood this. So now let's go with more bit detail part over here. What is this xi star that I'm saying? Right? What is this xi star? Over here, when I was doing this, when I did it, right? F of a into what? What did I do? F of into h, right?
into
So
Yes,
what did I
F
do?
into H.
I took this as my height, right?
yes.
I did not take this as my height at that time. If I was taking this as the height, what would be my area? This would be my area. This entire thing would be my area, right? But you would have asked me, why didn't you take that as your height? It would have still given you, but in that case, I would have overestimated my area.
Overestimated. Yeah.
Right? I would have overestimated at that point of time. But you can also tell me, why don't you take the central value then? Take this as your height. I hope I have scribbled it a lot there. Maybe I can just redraw.
Understood, sir.
You understood, right? So now you, yeah, I know you understand, but I want all of you to understand. So maybe I can just take this as the area. Okay. So now you see this. This is my f of, sorry, this is my a. This is my f of a, and this is my h. So this is going to be a plus h. So this is going to be f of a plus h, right? Likewise, you have it more. So you know it goes on. So now all I meant to say was, if I'm finding the area, I can also take this as my thing. No, why should I only take this f of a or f of a plus h, right? I can also take something in between. So that is what this tells you. This xi star tells you that your basically your height need not be this height only. Need not be this height only. It can be height over here too. This is what it tells. When I take the height from here, then you find the area, then what happens? This will be area. When I take it in the center, right? When I take this as my xi star, when I take this as my xi star, then this is going to be my area, right? When I take only this as my height, then this was only my area at that point of time. And when I was taking this as my height, this as my height, then this entire thing was my area, right? So then you can claim me that, yes, you can say that this xi star could be anywhere. It can take this side. So you can say that this could be this one, or this can be this one, or it can be the central one, the average of these two. You can take any of these. Could you tell me which will give you the best estimate of the answer?
The middle one.
The middle one is
Average.
something we claim, but
The closest to the starting point.
so the see that is actually hard to say just like just by looking at things, because it
Yes.
depends on the curve.
Yes, depends on the
Whatever curve it is.
right.
Yeah. So likewise, you cannot just claim that okay, this you better use the lower limit or better use the higher limit as your xi star. It can be anything. Okay. So in question, we also tell you your xi star is something. Your xi star is take xi. Xi is you take the lower limit. Okay. Oh, sorry, the upper limit. And when I say or xi star could be what? Xi minus 1. This means the lower limit. You remember these two pillars I was talking about? So this is your xi minus 1 and this is your xi. So what am I saying is take your xi star to be this one. Basically, when you are calculating the height, take this one as your thing, right? Or you can take this also. So in the question, we claim that, okay, you can use this. Or you can even say that take xi star is average of this. That is xi plus xi minus 1 by 2. I'll just say that, yeah, you take it in this way as well.
Sir, we can
So
even
how do you know that which one will be the most accurate?
That is something you cannot say it. But in question, we just want you whether you can apply this formula or not. That is, of course, it depends on the figure. So we cannot just tell you, okay, we cannot claim it in a way that this is what you have to do it. How do you get it is something you will understand when you are coming to more definite integral or like the actual integral, because that will give you the best integration value. So with Riemann sum, you cannot say, you can just roughly you can give you the answer. So roughly it could be anything. So that's okay. That's fine. No problem. But over here, all I want you to understand is what is this xi star? Now I hope you understood. Xi star tells you that what value you put so that you can take the height of a triangle, right? And that is something we'll tell you in the question. You choose your xi star to be something like lower limit or the upper limit or the average of both, right? And delta xi to this is nothing but what is the width, right? This talks to you about the width. So we also tell you, okay, fine, take this is your width. Or maybe when we tell you this one, all you have to do is subtract one from the other, you get the width. Okay. Now just be with me. We understood what Riemann sum is. Okay. Now we understood this part. We also understood this part. Now let's come to this one. What does this norm of P tells us? Okay. So what does this norm of P tells us? So what does this tells us is basically, look at this hint. Delta xi was nothing but width. And I told you in the very beginning that width did not be of same height. So when I'm taking this as my curve, I'll take one of my width to be this one. I will take another width to be this. So if I say this is h1, this is my h2. It need not be of same size. It can be of varying size, right? So over here, what does this norm P tells you is, it tells you maximum width. Over here, what is norm P?
H2.
H2. It simply tells you what? Whichever is the maximum width, that is your norm P. Understood? That's all. Nothing much. But it looks complicated, but it just tells you this. Understood? No doubt in here?
So,
We
sir,
understood what?
we will be given this max width.
Everything will be given. See, most of the question, the width will be fixed. It will be what? It will be some fixed value only. It will be fixed value in the sense the width will be not of
the
varying
width h that will be fixed, no? That can be varied from
But in the question, we can always change that. I mean, we can always say that the width is something different.
Okay.
Depending on the interval, what interval I'm taking. Over here, if I
But
take
interval
different
will be fixed. If the x plus h, the thing that will be fixed, right? So the rectangle we are measuring, the h has to be fixed. We cannot vary h because then the whole calculation will get messed up, no?
So we want you to give questions like that so that your calculation get messed up. So it's not going to be that difficult, don't worry, but we will make sure that you can understand this. When I'm giving you one question, you will be able to answer it just like this. This actually, the definition is difficult. You don't worry about this. Now you see, now I'm just going to tell you that.
Can I please explain that P thing once? Max I is the h, the max of h into delta xi, right?
No, it's not into. It's a max of delta xi.
Which one is maximum?
Whichever is maximum.
Okay,
So
okay, got it.
over here, maybe I can just tell you again. So if this is your H1, the width, I'm talking about the width. If this width is H1, this width is H2, let's say this is 1, okay? This is 2. And let's say this H3 is 3. So what is
Then we
norm
should
of
take
P?
3.
What is norm of P?
3.
3. Because you have to take the maximum of this width.
Okay.
That's all. That's all.
Oh.
That is
Sir,
more than.
sir, after taking the maximum of it, then we calculate the area. Like,
No. You don't do this. Do you see anywhere here norm of P in your formula?
no.
No. So you don't do that.
So why we?
I'll tell you why we do this. Okay. So now understood this. Riemann sum is just this much. That's all. In Riemann sum, this will be given to you. This is something you can find out with the interval. This xi star will give you. Now all you have to do is find out what is your function. Substitute it. Just multiply up to how many, like some 5 interval maximum we can give you, because even we have to stick down to the time, right? So 5 interval maximum we can give you. Okay, this is what. And we cannot give you complicated function also if we are giving Riemann sum, because the calculation will become lengthy, right? And the purpose should be just to check whether you can solve the questions or not, whether you can apply this or not. That's all. So you can understand this. So Riemann sum is easy. Now I think you can understand this. Now what about this interval when we say? Now this comes, and what is this relationship between these two? So now I'll come to this part. Most of the time we know this when we write integral f of x dx. Now how is this related to Riemann sum, right? So for this, you can just write it down. No, it's given here, right? So you can just write it down. This limit a to b f of x dx is actually equals to limit norm of p. Now here comes this. The norm of p tends to 0. And what is this SP? SP is Riemann sum, right? SP is Riemann sum. From here we are getting this. So it says what? Now I'll come to this part, don't worry. So limit norm p tends to 0, s of p is actually equals to what? Limit n tends to infinity. Okay, maybe I can just tell you I can go this way, then you can understand this. You know this, what does this tells you? What does this gives you? This part.
Riemann sum.
So this gives you Riemann sum.
Mm.
All of you are with me?
Yes, sir.
So this is giving me Riemann sum. So this is my S of P. This is my Riemann sum. Now you see in Riemann sum, when I say this n, right? 1 to, I'll be explaining you over here. When this n tends to infinity, when this n tends to infinity, right? What happens to your interval? What happens to your, let's say, what was our interval h, right? Okay, maybe I can just write down. N tends to infinity. What happens to your h?
It tends to 0.
It tends to what?
Infinity.
0. Then
0.
if this h tends to 0, what does your norm p tends to?
0.
0.
0. All of you
No,
agree?
sir.
No?
I don't. I
You lost it. Okay, no problem.
I
You
can't get
understand?
that point.
Okay, fine. Come to this Riemann sum. Understand this Riemann sum, okay? You understood Riemann sum,
Yes.
that I know.
Yes.
If I increase this, you remember when I do this, and when we were drawing this triangle, and here we had our h of n. When this n is very large, let's say n is infinity.
Yes.
What is happening to your this interval? Is it
It
reducing?
tends to 0.
Tends to 0.
Yes.
What was your norm p? Norm p was
Sir,
maximum
how
of
it
this
tends
interval.
to 0? You told that it vary and it gets larger.
Whichever is larger, it still tends to 0 only, no?
Yes.
Whichever is larger, it still tends to 0, isn't it? I'll
Got
explain
it.
You see this, even though let's say uneven intervals, okay? You had this uneven intervals.
Yes, sir.
Then you had this uneven intervals. Let's say over here also. This is H1, H2, H3, H4, H5, H6, H7. Okay. So now what I'm saying is this interval, initially it was up to till H7. Now I'm saying now increase it. Now increase the interval. Now if I say make it Now here n is what? N is 7. N is 7 in the sense, basically, this is xn, right?
Yes.
Right. So now what I'm saying is, let n be very large. Now let's say n is 14. Now what happens when n is 14? This interval will divide into 2. This will become half. This will become half. This will become
Yes.
half. This will become half. This will become half. This will become half. Now I say you make it 28. This will further reduce. This will
Yes,
further
sir.
reduce. So you see this, the larger interval is also decreasing. If the largest width is tending to 0, what about the smallest width? This is also tending to 0, right?
Yes, sir.
So that is why we should focus the largest width, because if the largest width itself tend to 0, the smaller width I need not worry, because that would have always tend to 0, isn't it? That's why this norm P concept has come. Understood?
Yes, sir.
This will tell us that if the larger width itself is tending to 0, then definitely the smaller width will go to 0, isn't it?
Yes.
I hope you understood. Understood?
Yes,
so now let's understand this.
Yes, sir.
So now in this Riemann sum, when n was tending to infinity, the width was becoming very, 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 very smaller, and it was tending to 0. When that width was tending to 0, then your norm P is also tending to 0, and I just explained you why is that happening. Okay. So now let's go with this. Over here, this was giving me Riemann sum. And when n tends to infinity, that means it's becoming very finer and finer and finer and finer. That is essentially this limit norm P tends to 0 S of P. Now you can understand this. I'm just going to
Yes.
say.
Yes.
Now, when you do it for that finer particle, that essentially means this. When you do it for a very, 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 very small interval, that essentially means your integral a to b f of x. Now you can understand this, comprehend this better.
Yes. Got it.
All of you understood?
Yes, sir.
Okay, got it. We will not go to this one, this piecewise and other things. I think I took it by mistake, so we will not go with this part. This is something you can understand. This is basically a method of solving questions. So that's fine. But over here, for understanding the concept, we understood this. Okay, now let's do some problems so that we can comprehend this better. So we are out of time, but we can still discuss some 3 problems which I have it here. Okay. Now consider this is question 1. Consider an interval from 10 to 35. Now what? Think of this way. This is what 10, and this is what 35. Okay, so now always, I mean, just for the explaining purpose, I am telling you this is my 10 and this is 35, right? So this is the interval that is been given to me. And now you see the partition says what? Whenever it says partition, that means what? This is what it means, partitioning. Okay, so partitioning says you what? X0 is 10. It says what? X0 is 10. So this is my X0. X0 is 10. And what is the last one? X5. Which is what? X5 is 35. Okay. And in between, I have some X1, X2, X3, and X not blah, 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 whatever. Here they are saying, okay, X1 is what?
15.
15. So X1 is what? 15. So can you tell me what is the width over here?
Five.
X1 minus
5.
X0.
5,
so this is
sir.
basically delta Xi, right?
Yeah, delta x. This is
So this is
5.
going to be 5. Now let's check whether this is uniform delta or not. Okay.
No, this is not
So that is
uniform.
something we can check this. So maybe we can draw that here and understand this better. Okay. So we have one question on non-uniformity. So let's discuss that. So over here, this is what? This is 5. The width is what? 5. And this is X1. Now what about X2?
90.
Maybe I can just write down all the things. X3 and the last one was X5. So this is my X4. So maybe I can just extend it. So this is nothing but 15. What about X2? X2 is 19. So could you tell me what is the width? All of you can quickly solve this and tell me.
4.
What about this X3?
7.
What is
7.
X3 by the way? 26. So this is 7.
And
what
next
about
one
this?
is 5.
This is 31, right? So this is going to be
5.
26. Yeah. Yeah, this is 5. And what about
And
this?
next one is 4.
Next one is 4. Okay. So now what is norm of P here?
7.
7.
So now you understand this. Norm of P is 7. All right. So now you can understand. Define this. You can tell this. You can tell it by, you can tell me easily. Okay. What is delta Xi? That is varying. That is something we found out. This. Now if I have to tell you find the area for this, then how will you do this? You actually cannot do it because your function value is not given. Okay.
Yes, sir. Function
Right?
values.
So if I say function value is x, f of x is x.
Okay.
Then summation.
Then what do you do? And again, then I have to tell you, okay, what is my xi star?
Yes.
Let's say xi star is x minus 1. So I minus 1. I minus 1 means you have to take this interval. Basically, this site, this area you will find out. So can you tell me what is the area for this? I'm just doing my Riemann sum. Okay, so let's do it. So S of p is what? Summation I to 5. I equals what? 0 to 5 maybe, right?
Right.
And what does it say? F of xi star into what? Delta xi.
Delta xi.
Right?
We have calculated.
So delta xi is varying, so we can find out that varying thing. But xi star I have to fix. What I'm saying, xi star is the lower one,
Yes.
x minus 1. So if I have to find out, so maybe I should tell that I'm starting from 1. So when I have to do this, so what is f of 1? So f of 1, so sorry, no, f of 0. You have to go with
F of 0 number because xi is
so
To start from f of 10, 10, right?
Yeah, f of 10.
Sorry, what?
We have to start from 10. F of 10 is the height.
Right. So what you will say that the height is 10. Okay?
Yes.
So from
And
here
the
you get the
width
height
is
is
5.
10 and the width is 5 plus, maybe I can just use this. What about the other one?
15 into 4.
15 into 4.
15 into 4 plus
19 into 7.
19 into 7. 26 into 5.
Wait, how are you saying? Okay, you're just substituting that. 19 into 7.
7. 26
Plus-
into 5.
And likewise,
31
you can do
And 31
35.
into 31 into 4.
31
35
into
y.
X,
31 it will be na?
xi minus 1.
And then that's
30.
it. No, you will not be doing that.
And
Yes.
then it's
Because you are
done.
taking
I
the lower
think
triangle.
it's finished, na?
Yeah, it got finished.
Yeah.
Okay, so now you understood that. Now all you have to do is
Yes,
multiply
sir.
and sum, and you get this Riemann sum for this, and you get some value. Okay, so over here for this, like the main thing that you had to understand from here was what is this norm of P, and I think you understood what is norm of P.
Yes,
Right?
sir.
That is
Totally.
something you had to take from this particular question. So you understood that.
Yes.
Yes, sir.
Okay. So now let's go with another question on this Riemann sum type 2 question. So now here we have something like this. So let f of x be 3x plus 1, then find the value of integral 0 to 2 f of x dx. Now, first of all, they're telling you to do this, right? So could you tell me what is integral 0 to 2? F of x is what? 3x plus 1 dx, right? So could you just tell me quickly what is the value? From here, I get 3x square by 2 plus x, correct?
Yes.
And then I have to substitute this limit 2 to 0. So this is going to be what? This is going to be 3 into twice 4. So this is going to be 6.
12.
6 plus 2.
It's a little bit slow.
Okay, little bit slow. Fine. No problem. So now you just have to substitute this value. If you substitute this 2 first, so this is going to be 2 square by 2 plus 2 minus this entire thing. Now this is going to be 3, 0 by 2 plus 0. So what do you get from here?
So sorry to interrupt you. I got it up to the integration you have done. Then which value you are putting as the xi 2i by n? I didn't get that.
Come again. Sorry, what?
The integration part, I got it.
Okay, you got
And
the
then
integration.
what the value you are putting?
These, the limit value.
The limit value you are putting. Okay.
So I wrote this 2 over here and 0 over here. So it essentially means what? When you integrate, let's say you get some function f of x. And then it means that you have to do f of 2 minus f of 0.
That
And
value.
whatever you
0.
get is nothing but your integration.
Yes.
So from here, that is what we did. So we first integrated it, and then I'm substituting this 2 for this entire thing. So I just substituted that. Then I told you that you have to minus, right? So then substitute 0 and then minus, and then you get the answer as 8. So it tells you what? Let f of x be this. It's given with the function. Then find the integral value for this using the limit of Riemann sum as n tends to infinity for given partition P. Now over here, partition is also given. Over here, partition is also given, and your interval xi is also given. Look at this, xi is also given, right? You notice that?
That was a uniform partition, right?
This is uniform partition, because you can understand from here itself. So it's a uniform partition. So what is delta xi in this? 2 by n.
Yes, 2 by n.
Right? And what is xi star? 2i by n. And how do you get Riemann sum? From I equals to, it says, no, from n tends to infinity. Over here, they says that limit n tends to infinity. So this is n tends to infinity. F of xi star times delta xi. Right? This is what it means, isn't it?
Yes.
Okay. So this is my Riemann sum. But again, here it says what? The moment it gives that n tends to infinity, here when n tends to infinity, something should trigger in your mind that if you just find this, it will suffice the need.
Partition reduces to 0.
It tells you what? See, this question was simply to confuse you that you can actually get answer with definite integrals, and you can also get answer with your Riemann sum formula. But which is easiest to do? The one which you know the formula, right? If you know how to solve it with the formula, you can just get it in 2 steps or 3 steps. But in Riemann sum, when you're taking Riemann sum, this question was just to confuse you that when can you actually use Riemann sum and when cannot you use Riemann sum. You understood, we wrote this very definition that integral a to b, right? F of x is actually equals to what?
FB minus.
We actually wrote this, you remember? Limit n tends to infinity. Your Riemann sum was what? Like Riemann sum formula. So f of xi star delta xi.
Delta xi.
So if this was the case, then I can actually do this instead of finding Riemann sum.
Sir, I have a question. Means, can you explain that partition P, how interval is working?
Over here?
Yeah, that given partition P, 0 is equal to x naught, comma x1.
I'll tell you that. Okay, I'll explain you that. But you first understood, no? Why we are actually doing definite integral but not Riemann sum?
Since n is tending to infinity, the sum will
then you can directly use this. But if n was not tending to infinity, let's say if it was going to 5 or something, then you could not have used this formula. If you were using the formula and you were giving answer as 8, we would have given you 0 marks for that. Let's say if n was not 5, if n was not infinity, then yes, you should have actually done Riemann sum. This was just to confuse you when you can use Riemann sum and when you should use definite integral. Okay? Right? So understand this. So now you asked me this, right? So you can tell me over here, what is your x0? 0. What is your x1? 2 by n.
2 by n. Sir, can you show the question?
Here. Use this, no? Xi formula, you can see this.
Wait a second. Okay, I just zoomed in. So it
then if I equal to 0, it will be 0. I equal to 1, and so that thing is going on, right?
Yes.
So what about x2?
4 by n.
4 by n.
Likewise, what is your x3?
6 by n.
6 by n.
Like that. Could you tell me what is the interval for this?
2 by n.
What about this?
2 by n.
It's the same. For all, it's same.
Like this?
It's the uniform.
That's why I told you can actually figure out what is this, right?
Yes,
so you see this delta xi is fixed over here. Okay. And what about xi star? They are telling you, okay, use this as your xi star.
Yes.
Okay. Use this as your xi star and then solve it. You understood?
Okay,
Yes,
sir. But basically, I was not getting how this partition is going.
No problem. Okay. So now having known this,
so whenever the n is in the limit is infinity is given, n is infinity is given, then we will use the normal integration.
Yes.
Okay. So could we use Riemann sum also once and check this out?
Yes, sir. Please
Let's
show.
do with the Riemann sum also.
Yes, sir.
So how do you do with the Riemann sum? So you see this, Riemann sum formula tells you what here limit n tends to infinity. We should get the same answer even if we are using Riemann sum, right? This is
Okay.
what we are saying. But this is a bit lengthy process, but still doable, right? N tends to infinity. But again, what is my f of xi star delta xi, right? This is what it means. Now I'll just simply substitute the formulas. So fi, so what is my function? 3x. Xi star is what? I can just simply write down here. Xi star is 2i by n. 2i by n. And what is my delta xi? 2 by n. So now I can just simply substitute this. So this is my function, right? So, and there is a summation symbol from 1 to, from basically, so 1 to infinity, or like it does not go to infinity. It actually goes to 1 to 2.
n.
I goes to n, sorry. Yeah, it does not goes to infinity, and n tends to infinity.
Yes, sir.
Yes. You got it.
So what about this then? So f of, so this is going to be 3x plus 1. So I can just simply substitute this xi star. What is my xi star? Instead of x, I will just write down 2i by n plus 1 as it is, right? And delta xi is nothing but 2 by n. Correct? This is what it means, no?
Yes.
I equals 1 to n. Now let's do some kind of simplification here. So this 2 by n, let it be as it is. Now look at this. I is the one which going to n, right? So this I can write it as, if I'm just simply simplifying this, so this is going to be 6 by n I plus 1 upon 2 by n. Can I write it in this way?
Yes, sir.
Yes, sir.
Right? And still over here, this is still there. I 1 to n, and of course I should not forget that limit n tends to infinity. Over here also limit n tends to infinity. Now look at this. What is this I? I is increasing up to what? Some natural number. So it's going to be 1. Then in the next case it will be 2. Then it's going to be 3 plus 4. This I, right? When I is 1, so I'll get 1. When I is 2, then this will become 2. Then 3, then 4, then 5. So maybe I can just further do this. Limit I tends to 1 n. So I can simply simplify this and write down 6 by n, and I can simply multiply this by 2 by n I. Right? I can do this.
Yes.
Plus, I can do the same thing over here. Limit n tends to infinity. I'm just multiplying this and separating them apart.
Separating limit. Yeah.
Right? So now what
2 by n.
Limit summation I equals 1 to n. This is going to be 2 by n.
Yes.
Okay. So now let's do this. So now there are two components over here. This one. We should have not gone with this. We could have actually solved it here, but this is just to explain you I'm doing this. Okay. So this is actually going to be 6 times 12, 12 n square, right? So I can just simply write this as 12 n square. Now what happens? If I just expand this, so 12 n square will be outside. When I is 1, so 1, then 2, then 3, then 4, then 5, and this is summation then up to what? N, right? What about this?
N.
N tends to infinity. Summation 2 by n. So 2 by n, how many times am I adding?
N times.
2 by n plus 2 by n plus 2 by n plus 2 by n up to n. Right? It goes up to that thing. So now you know that this is sum, and sum of n natural numbers. There is a formula.
Yeah, n into n plus 1 by 2.
N into n plus 1 by 2 will actually give you this. When I'm adding all these, I get this. There is a formula, so you can memorize this. So this is going to be 12 by n square. So this I can write it as n into n plus 1 by 2, right? Now my limit, you see this summation symbol is gone, but still my limit symbol is there. Okay, yes. I did not remove my limit, so maybe I can just give limit n tends to infinity and keep this all together. Over here, what is happening? 2n plus 2n plus 2n plus 2n plus 2n plus what? It's going up to n, so I can write this 2n times n.
Yes.
Right. Or basically, I can take out 2 by n common from here, then I'll be left with what? 1 plus 1 plus 1 plus 1 plus 1 plus, and that will be what? If let's say it goes up to 10, then if you add till there, it will be 10. So this will go up to what? N. So this is just n. So here n and n gets cancelled. Over here, this n and this n gets cancelled. Right. So what I'll be left with? And over here, this is going to be 2 ones are, and this becomes 6.
6.
So this is going to be 6n plus 1 by n, and this is just going to be 2. And still remember, I still have this limit n tends to what? Infinity.
Infinity.
So now what again? I can just expand this. I can just separate this. So this is going to be
Okay,
6
6 plus 2,
n
8.
by
Yes.
n, and this is going to be 6 by n, right? Plus 2. And again, what? My limit tends to infinity. So
Infinite.
this gets cancelled, right? So I'll be left with just 6 over here, right? So this is going to be 6.
And this is plus 0.
And limit n tends to infinity is what? 0.
0 and plus
This
2
is
is
going to
already.
be-
Okay.
So you see, there is many lengthy process when you're using Riemann sum.
But doable.
Doable. You need more practice because you can do mistakes. But all you have to understand from here is when n tends to infinity, all you have to do is use direct integral formula. So this is this kind of question. This is exactly the same question that I have taken from the end-term paper, and I just removed this. You see, this was the answer is 8, and this is exactly the same question that was asked in your end term, and I thought I could discuss here. Again, so many people were claiming. Yeah. Again, so many people.
The last part. The
Last part? Okay.
final part. Okay, sir. Thank you, sir.
Yeah. So again, so many of them were claiming that okay, the paper was lengthy, but actually you should have been smart here. That which method you should have used? This method. So when we took the
Integration,
review, then you
proper
were like,
integration method.
how can we use Riemann sum in this much time? So like you have to actually think that the examiner is just wanted to check you whether you can actually understand, you can comprehend that yes, that is something we are asking you to find out what? That you can find integration with direct integration also. Okay, that is what it is. So fine, this is all for today's session.
Sir, could you share this?
This written thing.
Yes, sir. Yes, sir.
I can share, but I think I have done a lot of errors. So if you're okay with it, I mean, if it is there any error, you can actually point that error in the forum so that even others can understand. Okay.
Yes, sir.
But I can share you this. No problem.
Yes, sir. Thank you.
Sir, my discourse hours is not updating. Whom should I contact?
Tag maybe Narayanan @Narayanan. You can tag.
Where can we see his handle?
Discourse, no? Your type.
Okay.
Sorry, what? What did you ask me? Sorry, I did not get it.
Actually, I asked means my discourse hours means how many hours I am spending. It is not getting updated. Means I spent around 2 hours yesterday, but it is still showing 33 minutes. Even interacted, solved some of the doubts there, asked questions also.
Okay. Fine. Maybe you can just tag TA there. TA community, one person comes, right?
Okay.
There is one TA who is assigned for this. So you can just tag that TA. He will take care of it.
Any TA?
Hi, you can just simply put that @TA, right? You will get that community TA tag, someone. You can just tag him. Yeah, he'll answer you.
Okay.
Yeah. Okay, fine. Then we can end our session and maybe I can share you the sheet as well. So thank you, everyone. Have a good day.
Thank you, sir.
Thank you, sir.
Yes, sir.